On Thursday, we talked about two properties of waves, namely diffraction, which is the spreading out of a wave around a barrier or through an opening. The wave strikes the barrier like this, goes through a little bit of an opening like this. It doesn't bend. That would be refraction. It doesn't change direction or change speed. That would be refraction. Rather, it spreads out as it goes through that opening. Diffraction, that's a property of waves. It's exhibited by EMR, as we learned on day one of this unit, so therefore EMR must be a wave. But we also learned about interference on Thursday. If we have two openings, then that wave will go through both of those openings at the same time. It will diffract from both of those openings at the same time. And where it overlaps, we will get a phenomenon called interference, which is also a property of waves, but is exhibited by EMR, therefore evidence to support the wave nature of EMR. Now, let's take a look at the interference pattern that we see here. Let's pretend these are water waves, where when we're looking at it from above, we can see the interference pattern. If we were to draw this out, every single place where one wave overlaps another wave or interferes with another wave, we would find that we would get a pretty recognizable pattern. We would get right up the middle a line of constructive interference. And then right beside it, we would get a line of destructive interference, where a crest met trough. And then constructive, and then destructive, and so on. Now on the other side, we get exactly the same pattern. It's very symmetrical. Constructive, destructive, constructive, destructive, and so on. If these are water waves, we can literally look at it from above, like we did the photo on Thursday, and see the interference pattern. But if it's light waves, which is of course what we're dealing with in this unit, we can't see this interference pattern. Light needs to reflect off of something to see it. So when we just look at it from above through the air, we're not going to see what we would see if it was water. So how do we see it? We put a screen in here. We put a screen down here. The screen will show us a version of the interference pattern. What we end up seeing is not all these little lines, but rather we see a bright spot where there was a line of constructive interference. And then we see we call it a dark spot, but remember what the dark spot really is? It's the absence of a bright spot. We see a dark spot right beside the bright spot, and then another bright spot, and then another dark spot, and then another bright spot, and so on. Same thing on the other side. Bright spot, dark spot, bright spot, dark spot. Do you guys remember what another name for a bright spot is? Bright spot or a bright fringe. It's another name for it, right? A maximum, yes. A max or a maximum. It's another name for it. No, you're close though. An antinode. All three of those words mean exactly the same thing. If we look back to our imaginary physics thesaurus, we would find all three of these grouped together. Okay? They're used interchangeably. You guys remember what the other names for a dark spot are? Yep. A minimum. Good. Or a node. Again, used interchangeably, so make sure you recognize all three of those. Now, this is what the pattern would look like. Bright spot, dark spot, bright spot, dark spot. If we were to represent this pattern as a graph, not what we physically see, but just rather as a graph representing what we see, then we might choose to plot a graph of intensity versus position. Intensity on the y-axis, position on the x-axis. If we did that, then the intensity right here would be highest, because that's a central maximum. And then we would have zero intensity. And then we would have intensity, high intensity, and then zero intensity, and so on. Everywhere where there's a maximum, you would have some intensity. Everywhere where there's a minimum or a dark spot, there would be zero intensity. Now, whether we're labeling the actual interference pattern that we see on the screen, or whether we're labeling the graph, we would label either one of those as having a central maximum or zero order maximum. a first order maximum right here, a first order maximum symmetrical on the other side, a second order maximum, and a second order minimum. We don't usually label, sorry, maximum, I should say. We don't usually label the minima, but if we did, we would label this one as 0.5. The first minimum is 0.5. The second minimum is 1.5. And of course, the same thing on the other side, right? Now, this is what it looks like if we have one color, if we have red light. But what if we have more than one color? What if we have, what's the word that we say means more than one color? Yeah, polychromatic, right? Monochromatic is one color, polychromatic is more than one color. If we have just red, then this is what we see, right? Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on. This is our zero order max, or our central maximum. First order, second order, third order, first, second, third order on the other side. If we say did this with blue instead of red, what would we see? Well, something that looks almost the same. Our central max would be in the same place. Our first order max would be a little bit closer to the central maximum. If you take a look over on the bulletin board over here where we have the poster, the Pink Floyd poster, we can see that red light refracts the least. Low frequencies refract less. The index of refraction for low frequencies is lower than it is for high frequencies. But if you take a look at diffraction, you can see that low frequencies or red light diffracts more. So you would see this pattern if we used just red. We would see this pattern if we used just blue. You notice the blue doesn't diffract as much. It's closer to the central maximum. Now, what if we did them both together? What if we had red and blue light going at the same time and diffracting and interfering? You see kind of a mishmash of red and blue together there. But then we would have something like this. Be careful. It's not like this is first order, second order, third order, fourth, fifth, sixth. This is our central. This is our first. This is our second. This is our third. Now, most questions that we get involve monochromatic light, but if you're given polychromatic light, then it's going to look something like this. But what I want you to do is just pretend you don't have more than one color. If you're looking to analyze just red, let's say, then pretend the blue doesn't exist. And we would treat it as if we just had red. If we just had blue, pretend the red doesn't exist and treat it as if you just have blue. Does that make sense? What do you see in the middle here? We said if it's red and blue, it's kind of like a hodgepodge between red and blue. If you had all the colors of the rainbow, what would you see in the middle here? White. Yeah, you'd see white there, right? You'd see here, you'd see a spectrum and another spectrum and another spectrum, multiple spectra. But in the middle, you just see white light. Okay? So prisms split up light, as you can see over here on the poster, red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. Diffraction gratings split up light opposite to that. Instead of Roy G. Biv, we get Viv J. Yor. Roy G. Biv backwards. Okay. Now, we learned on Thursday that we have two equations that apply here, d sine theta and xd over n times L. Lambda, of course, means the wavelength. Okay, that's the easy one, the wavelength of the light. What does d stand for? D in both of those equations means the same thing. Yep. No. It's the distance between the slits, distance between one slit and the other slit. The distance between the slit and the screen is going to be L. And sometimes we make that a capital L. Doesn't really matter though, capital L, lowercase l. Remember that L, that's the biggest number. You're going to be given a few different numbers here in these questions. L is the biggest one, and that's always going to be the distance from the slits to the screen. X, oh, this is the one, right? This is the one. It's weird. X could be this distance right here. It's always a distance, not a number, a distance. Could be this distance from this maximum to that minimum, or it could be this distance. Doesn't really matter, as long as n is consistent. In this case, we would say n is equal to 1. 2 minus 1 is 1. Here we would say n is equal to, what's that one? You're going from the first minimum to the second maximum, n would be 1.5, right? 0.5, 1, 1.5, 2, 2 minus 1.5. What about this last one here? Somebody this morning in both classes actually said n is equal to 0. But somebody in both classes also said n is equal to 3. So which one is it, 0 or 3? It's 3. Yeah, the difference in the maxima is 3. We're going from 1.5 to 1.5. We'd say 1.5 minus negative 1.5. Okay? It's not the same maximum, it's not the same minimum, so it can't be 0. All right, finally, theta. Theta is the angle, as always, measured from the central to the second order maximum, where n would be 2, or from the central to the, well, pretty much whatever you want, to the second order minimum, where n would be 1.5. But it has to be measured from the central to something, versus x, it can be measured from whatever to whatever. I won't tell you what this big if means quite yet, but I will soon. All right, we had 3 questions for homework. I want to take a look at those now before we worry about what that big if meant. Page 689, questions 1, 2, and 3. I want to take a look at number 3. Any others we want to go over here besides number 3? Number 1? Okay, 1 and 3? Okay, you good for number 1? Just 3? Okay, number 3 it is. It says the second nodal line of an interference pattern occurs at 0.095 relative to the central antinode. It can get a little bit confusing what n is here, so let's draw it out. Here's my central antinode, or my central bright spot, or central maximum. Here's my first order. Here's my second order. Here's my third order. And of course, the other side looks the same. I want to find the wavelength from the central to the second order nodal line. That would be this one, right? A node is a dark spot. The second dark spot. What's n going to be equal to there? 1.5, good. If it was the second antinode, n would be equal to 2. We got an angle here of 0.095 degrees. The slit's separation distance is 0.40 times 10 to the minus 3. This has got to be meters. Solve for lambda. We won't worry about the color here. Let's say lambda is equal to d sine theta over n, or 0.40 times 10 to the minus 3 times sine 0.095, a really small angle, divided by 1.5. See what we get here. Let's divide that by 1.5. We get 4.42 times 10 to the minus 7, or 4.4 times 10 to the minus 7 meters. We should be able to recognize that's visible light by converting it to frequency and comparing it against our known frequencies, but don't worry about what color it is. All right, let's take a look at that second equation now that had that big if. Remember, lambda is equal to x d over n times L if ... and I told you that I'd tell you what that big if meant in a little while. Now I'm going to tell you. We know the variables here, right? X is the distance between maxima or minima. D is the distance between the slits. N just has to be consistent with X. L is from the slits to the screen. But what's the big if? Well, the equation that we've just used, d sine theta over n, is perfectly valid anytime. It is a good equation. It is derived exactly from the geometry of the interference pattern that we would find. This equation is actually an approximation. It's not actually perfect. Okay, we make an approximation as we're deriving this equation, but it's a really, really good approximation at small angles. When the angle is small, this works really, really well. Even though it's not perfect, it works really, really well. If theta is less than about 10 degrees, we say this equation is good. If it's bigger than 10 degrees, then the approximation becomes not as good. So we don't want to use this equation above about 10 degrees. But we have to have, or at least in my mind, we have to have a different way of determining whether we can use it or not, other than determining the angle. Listen, if we're given a question where we have the angle given to us, let's say it's 6 degrees. Well, why wouldn't you just use this equation? Lambda is equal to d sine theta over n if you're given the angle. Right? If we're told that it's 6 degrees, yeah, it's under 10 and we could use it with this, but why would we? If we're given that it's 6 degrees, why wouldn't we just use this? So this becomes useful if we don't know what the angle is. Maybe it's bigger than 10 degrees, maybe it isn't. We have to determine what the angle is in order to use this, to make sure that it's under 10 degrees. But if we have to determine what the angle is, well then why wouldn't we just use this? So what's the value of this second equation? Either we have the angle or we got to find the angle, right? Well, I have this little rule of thumb, and this is just my little thing. So if you ever go on and take this in university, you probably won't see this little thing, but it'll still work. Okay, even though somebody else might not teach it to you, it'll still work. My little thing is a rule of thumb. The rule of thumb is this. Is L greater than 10 times X? If it is, then the angle will be less than 10 degrees. So in other words, we can determine whether this equation is valid or not without bothering to determine what the angle is. We may not know what the angle is, but at least we know it's less than 10 degrees or not. We know that we can use that equation or not. Is L greater than 10 times X? So if you have a value of X and it's 0.5, 10X would be 5. If L is 6, you're good to go. If L is 4, then you're not good to go. This equation couldn't be used. You'd have to find the angle then and use the other one. I'll show you how to find the angle in a little while. Okay, let's take a look at an example here that's based on that equation. 13.9 on 691, it says a student measuring the wavelength of light emitted by krypton gas directs the light through two slits separated by 0.264 millimeters. Interference pattern is created. The screen 3 meters away. Here's the distance. What's one of the wavelengths of light emitted by krypton gas? What are they kind of telling me if we read between the lines there? What is one of the wavelengths? There's more than one. But one wavelength will produce this data. Another wavelength will produce different data. What did I say to do if you have more than one wavelength? Pick one. We're going to pick this data and we're going to get the wavelength that's associated with this data. Right? It doesn't matter that there's more than one color. We have data for one. Let's go with it. So what do we got here? We got D is 0.264 times 10 to the minus 3 meters. 0.264 millimeters. L is 3 meters. We're going to say N. We're going from the second bright spot to the central. N would be equal to 2. And X would be 1.18 times 10 to the minus 2. Or you could say 0.0118. What happens if you go to xd over n times L if theta is greater than 10 degrees? Is theta greater than 10 degrees? I don't know. I don't know what theta is. So let's do our little check. It's 1.18 times 10 to the minus 2 because it was 1.18 centimeters, and we want to convert that to meters. Okay, what's the value of 10x? X was 1.18 times 10 to the minus 2. 10x is 1.18 times 10 to the minus 1. L is 3. Is L greater than 10 times x? It's way bigger than 10x, right? Somebody this morning said, what if 10x is really, really close to L? Can we do it then? Yes. This little rule of thumb that I've come up with errs on the side of caution. So even if 10x is equal to L, you're still good. Just don't use it if it's greater than L, that's all. Okay, so we're good. We can use this equation. X is 1.18 times 10 to the minus 2 times D, which is 0.264 times 10 to the minus 3. N is 2, and L is 3. (1.18 times 10 to the minus 2 times 0.264 times 10 to the minus 3. We're going to divide that by 6. 5.2 times 10 to the minus 7. Good there? Quick question though. What would we have done there? What would we have done if 10x was 3.1? What if L wasn't greater than 10 times x? Right? Find the angle. Yeah, just find the angle. This would be x, the distance from maximum to maximum. This would be L, the distance from the slits to the screen. This would be theta. Just find the angle. We could do that every time, but if we do that every time, then why wouldn't we just use the other equation, d sine theta over n? Okay. By using this little trick right here, this little rule of thumb, we avoid having to do this most times. The only time we have to do this is if L is not greater than 10 times x. If it's not, find the angle and then use the other equation. All right, I'm going to give you a few minutes here to work on 3 questions on page 691. Be careful on these. Pay attention to little things like third dark fringe, central antinode, 0.5, whole numbers, 0.5s, whole numbers, 0.5s. Okay, watch out for little things like that, okay? See what you can do here. Last example for the day on page 693 says a diffraction grating has 1,000 lines per centimeter. What does that mean? Well, this is a diffraction grating where you have 2 openings, right? We also call that a double slit experiment. Specifically, it's sometimes called Young's double slit experiment, named after a guy named Thomas Young who did this experiment first. 2 slits, diffraction grating, whatever, right? The distance between those slits is, of course, called little d. Now, a diffraction grating is more typically a term that's associated with a situation where you have not 2 openings, but lots of openings like this. Maybe you have, as in this case, 1, 2, 3, 4, 5, 6, 7 openings, or maybe you even have 1,000 openings per centimeter. A diffraction grating has multiple openings, usually more than 2. Now, the distance between openings is still given by the symbol d, but we're not typically in one of these questions given the value of d. Rather, instead of being given the centimeters per line or centimeters in between lines, we're given the lines per centimeter. So as opposed to this value being d, this value would actually be 1 over d. Right? Centimeters in between lines is d. Lines per centimeter is the inverse of d. So what do you do to get D? All you're going to do is say D is equal to 1 over 1,000. When you calculate that, it ends up being 1.00 times 10 to the negative 3 centimeters, which we want to convert to meters. So we're going to make it 1.00 times 10 to the negative 5 meters. If you got lines per centimeter, lines per meter, flip it over, get D. Because you've got 1 over D, get D. And then convert it to meters after that. So there's the value of D. When light passes through the degrading and interference pattern is produced on the screen 4 meters away, this is L. The first order bright fringe, central, first order, middle, N is going to be equal to 1. X is 19.2 centimeters, or 0.192 meters. What's the wavelength? We won't worry about the color. Want to use this equation, but can we? X is 0.192, multiplied by 10, 1.92. L is 4. Is L greater than 10 times X? Yeah. So it's okay to use that one. X was 0.192. D is 1 times 10 to the negative 5. N is 1. L is 4. So we go, we're going to say 0.192 times 1 times 10 to the negative 5, divided by 4, 4.8 times 10 to the minus 7. Remember, if L wasn't greater than 10 times X, then find theta. Find theta using this. Here's X, here's L, here's theta. Tan theta is equal to X over L. And then use the other equation. That's it. These questions aren't any different than the 3 questions you were just working on, except that you got to convert 1 over D to D. All right, 3 questions to go along with that on page 693. But I'm going to caution you. Question number 1. Be really, really careful with your comparison here, L. Okay, be really, really careful with that. And I'll also caution you that the answer for number 1 that's given in your book, it's not listed down here, but the answer that's given in your book is incorrect. The answer for number 1 is incorrect. So what are you going to work on right now? Page 691, what you were just working on a few minutes ago, and page 693. Those are going to be due for Wednesday.